Hello students, this is lecture 3 of MTH 201. In the last lecture, we looked at dot product of vectors, length of a vector and distance between 2 points, dot product and angle between vectors, their relationship, Cauchy-Schwarz inequality, and the concept of orthogonality of vectors. In today's lecture, we are going to focus on primarily two concepts. One is the projection of a vector onto another, and second is cross product of two vectors. So let us begin with defining orthogonal projection of a vector onto another. So let V and W be two non-zero vectors with angle theta between them, where theta lies between 0 and pi. So in the above pictures, I want you to focus just on the vectors V and W. Okay? And this is the angle theta between them. So the angle is acute. This is the picture that you get. Whereas if the angle theta is obtuse, then this is the picture that you get. Also, there is a third case when theta is pi by 2, in which case I have not drawn the picture, but they will be perpendicular to each other, right? So, what is orthogonal projection? From the terminal point of V, which is in, let's say, the left hand side picture, it is this point, the end point of the vector V. Drop a perpendicular on W, which is what we have done. We have dropped a perpendicular on W. And this vector that you see in the red, which is basically the vector which starts from the beginning point of V and W till the point where this perpendicular hits the W vector. Okay, so this vector P is known as the orthogonal projection of V on W. Now, when theta is acute, this is the picture. When theta is obtuse, what happens is when you drop a perpendicular, it actually hits this vector in the negative direction, right? Okay. So what is the negative direction for the vector W? It's minus of W, right? And what is the projection vector? It's this vector that you see on the negative W direction, right? From this point to here where the perpendicular meets this line or vector, right? So let us find out first the length of P and then the vector P. Okay. So if theta is acute, you want to find this length, which is nothing but the base of the triangle, right angle triangle this, with angle theta and hypotenuse norm V, right? Norm V is the length of the vector V. So what is the length of P then? Length of P is nothing but norm V cosine theta by using uh, right angle triangle formula, right? So norm V cosine theta, but then using the relationship between cosine theta and dot product, this reduces to V dot W divided by norm W, right? So this is the length of this vector P when theta is acute. Now the question is, what is the vector? So if you look at the direction, it is W, right? So what is the unit vector in this direction? It is given by W by norm W. So we saw in the last week that if you divide a vector by its norm, if the vector is non-zero, you get a unit vector, right? So, and that is the unit vector in this direction. So then what will be this projection vector P? It will be the length of this vector times the unit vector in that direction, which is W by norm W. And if you put these two things together, you get V dot W divided by norm W square times W. So this is the vector that you get, right? Else, if theta is obtuse, which is the picture on the right, then what is the length of this projection vector? It's norm V cosine pi minus theta, right? Because this is the triangle that we are looking at. But what is cosine pi minus theta? It's minus cosine theta. So you get minus of norm V cosine theta. And again using the relationship of cos theta and dot product, you get this equal to minus V dot W by norm of W. Right? So this is the length of the projection vector. Okay. Now, but in this case, the projection vector lands in the negative direction of W, right? So what is the unit vector in that direction? It's minus W by norm of minus W. But norm does not care about the negative sign, so you just get norm of W. Therefore, the projection vector equals the length times the unit vector in that direction, which is this. If you put things together, you again get the same expression that you got when theta was acute, right? Because this negative negative makes it positive. Okay. So to summarize things, let V and W be two non-zero vectors. The orthogonal projection of V on W is given by the vector this, right? And the length of the projection vector P is this we saw in the previous slide, right? So here I have put a modulus in cosine theta because you know that length has to be a positive number, right? So in the previous slide also we got positive numbers, right? When theta was acute, we got a positive sign. Cos theta is positive there. When theta is obtuse, then we got negative sign there. But we know that cosine theta is negative when theta is obtuse. Therefore, negative negative makes it positive. So therefore, I have put a modulus here without talking about whether it's acute or obtuse. In both the cases, this formula works. Finally, when theta is pi by 2, which means u and v are perpendicular, v and w are perpendicular to each other, then the projection, there is no projection, right? When you drop a perpendicular, v is already perpendicular to w, so you get zero vector. So the projection vector is the zero vector and therefore its length is 0. And therefore the above definitions are consistent with this fact, right? Because if V and W are perpendicular, then V dot W is 0. So you just get P equal to the 0 vector. And here also, of course, cosine theta is cosine pi by 2, which is 0. So you just get 0. So these definitions are actually independent of what the value of theta is in the interval 0, pi. It works for all values of theta. All right. So now let us look at an example of projection. I have deliberately chosen this example because theta is turns out to be obtuse here. Okay. So actually see that the projection is in the negative direction of W. Okay. And so these are the two vectors. I'm calling I plus j as V and minus 2i plus j as W. And since there is no k coordinate or z component in both the vectors, we have drawn this picture only in the xy plane for clear visualization. So now, if you look at these vectors, v is equal to I plus j. So what is the terminal point of v? It is 1, 1. That is how I have drawn this vector. Similarly, this is the vector w whose terminal point is minus 2, 1. That is how I have drawn it here. Minus 2 in the negative x direction and 1 unit in the y direction. Okay, so this is what you get. So now this angle is obtuse, but we don't have to really compute the angle in this case because we have formulas. So all we are going to use here are formulas, but I have chosen this example to illustrate that how the negative sign comes automatically. Okay. So let V be this, W be this. We know that the orthogonal projection of V on W is given by this formula. If you put everything here, what you get is minus 1 by 5 W. So it's in the negative direction of W. So this red vector that you see is basically the projection. And this green line is the perpendicular that you drop from the terminal point of V to the vector W. Okay, and it lands in the negative direction. What is its length? Its length is the norm of P, which is norm of minus 1 by 5W, which is norm of W divided by 5, which is equal to 1 by square root 5, because norm of W is square root 5. Okay. So this is one of the examples. You will see more example in the tutorial. Now let us move on to the concept of okay. So before moving on to the concept of cross product, let me talk about an important inequality which concerns length of vectors. Okay. So for any two vectors A and B in R3, length of A plus B is less than or equal to length of A plus length of B. And this is known as triangle inequality for a good reason. Okay. So let us look at this picture. So in this picture, OR is the vector B and OP is the vector A. And this is a parallelogram, right? So we know that A plus B is nothing but the vector on the diagonal, right? So this is your vector A plus B. Also, since it's a parallelogram, RQ is parallel to OP. Therefore, RQ, this vector is also the vector A, right? So you have this triangle OQR in which two sides are A and B and the third side is A plus B. Now, from basic geometry, you know that the length of third side is less than or equal to the sum of the lengths of the other two sides, right? So we already know that the length of OQ is less than or equal to length of OR plus length of RQ, right? What is the length of OQ? It's nothing but norm of A plus B. Length of OR is norm of B and length of RQ is norm of A, right? Therefore, triangle inequality follows from this picture. But let us prove it using the methods or the definitions that we have seen here. So you consider the square of LHS of this inequality. Okay. So what is norm square of norm of a vector? It's vector dot product with itself, right? Now, if you use distributivity, you get A dot A plus B dot A plus A dot B plus B dot B. But A dot B is equal to B dot A, therefore you get this term. Right? Now, using Cauchy-Schwarz inequality in the second term, you get A dot B is less than or equal to norm A norm B. Right? So this is where you have used Cauchy-Schwarz inequality. And the first term, A dot A is equal to norm A square. You have not used any inequality. It's actually equality. Similarly, B dot B is norm B square. If you complete the square, this comes out to be norm A plus norm B whole square, right? So if you take square roots on both sides, you get the triangle inequality, right? Now the question is, when is this less than or equal to sign and equal to sign? So let us look at the proof. So where did we use inequality? We only used at the place where we used Cauchy-Schwarz inequality. So when is Cauchy-Schwarz inequality an equality? When either A or B are zero vectors or A is a scalar multiple of B. So the same, for same reasons you will have equality in triangle inequality. If either A or B are zero, in which case you can see that they are equal, or when one is a scalar multiple of another. Okay. So now finally let us move to cross product of vectors. So let V and W be two vectors. The cross product of V and W is denoted as V cross W and it equals V cross W. I want you to focus on this part first. Okay. So this is determinant of some matrix. This is a notation where the first row are unit vectors I, j, k. The second row are basically components of V, which is the first vector that appears in the cross product. And the third row are the components of the vector W, which appears at the second place of V cross W. Now, I want you to calculate determinant of this matrix along the first row. So if you compute the determinant along the first row, it will be I times the determinant of this submatrix, which is this, plus you know the formula, right? You know determinants. And then you can compute these determinants. These are 2 by 2 matrices. Determinants are V2W3 minus V3W2 and so on. So V cross W comes out to be this vector. Okay. I'll again emphasize that ordering is important. If V comes first, then you write V in the second row, components of V in the second row. If W comes next, that has to go in the third. Okay. So using the properties of determinants, we can actually infer many things here. Okay. We will see that in a minute. So cross product is a vector as you can see, and it is also known as vector product. So like dot product gives you a scalar, a real number, and it's also called scalar product. Cross product gives you a vector and it's known as vector product. Let us look at a few properties of cross product. For all vectors u, v, w in R3 and scalars alpha and beta in R, cross product of a vector with itself is 0. This is immediate from the definition because in a matrix, if two rows are equal, right? If V is equal to W, so if these two rows are equal, then determinant is 0. So it just comes from the definition. I will not get into the other properties. You will see them in the tutorial. Let us look at this property that you see here, which is U cross V is equal to minus V cross U. This is also immediate because if you interchange two rows, determinant gives you an additional negative sign, right? Which is what you see here. Then the last property is called Jacobi's identity, and it can be proved using the second last equality, second last identity. So these properties will be discussed more in the tutorial. So I will not say more about it, but they all use properties from determinants because the cross product is defined using determinants. Okay. So now we are heading towards understanding what cross product means geometrically. Okay, and to do that we will introduce a concept which is called triple product. Okay. So given three vectors u, v and w, the scalar u cross v, so this is a vector, right, u cross v, you take its dot product with w. So what you get eventually is a scalar. This quantity is called triple product of these three vectors in that order. So ordering again is important here. If you say triple product of u, v, w, this is the order that is there. Okay. So what does it mean? So if u has these components, v has these components and w has these components, then u cross v dot w is what? U cross v is this by definition that we saw in the previous slide, and dot product with W. So what is dot product of a vector with another vector? It's multiplying the components and adding them. So you get first component of U cross V times the first component of W, which is W1, and so on. Now, this quantity is nothing but the determinant of this 3 by 3 matrix by expanding along the third row, right? So, if you compute the determinant of this matrix along the third row, you get W1 times determinant of this matrix, which is this, plus W2 times this, plus W3 times this. So, triple product has a very useful uh, uh, expression here, right? Now, you don't have to find U cross V and then take dot product with W. What you can do is, in the same order, you write the rows of this matrix. So, for if U comes first, then components of U is in the first row. Then if V comes second, components of V will be in the second row. If W comes third, components of W will be in the third row. And the determinant of this matrix is nothing but the triple product. Okay, so this is quite useful. So let us come to the geometrical interpretation of cross product using triple product. So in the previous slide, we defined triple product, and I'm going to use this term, this notation, because it's going to turn out to be very useful. Okay. So if W is any vector, the third vector, that is spanned by the vectors U and V, that is, there exist scalars alpha and beta such that W is equal to, I'm sorry, it should be alpha U plus beta V. I'll change it. So if W is a linear combination of U and V, or it is spanned by the vectors U and V, then what happens is that the third row in this matrix, which is W1, W2, W3, is a linear combination of first two rows. But you know that it's a property of determinant that if one of the rows is a linear multiple, a linear combination of other rows, then the determinant comes out to be 0, right? And hence this triple product is 0 whenever W is a linear combination of U and V, right? Therefore, U cross V is perpendicular or orthogonal to any vector which is spanned by the vectors U and V, right? If W is any vector that is spanned by the vectors U and V, or it's a linear combination of vectors U and V, then this dot product is 0. Therefore, U cross V is perpendicular to that vector, right? Dot product 0 means vectors are perpendicular to each other. So, we have this picture, right? So, U cross V is perpendicular to any linear combination of U and V. Therefore, in particular, it is perpendicular to both the vectors U and V. So, look at this picture. I want you to imagine U and V on the floor on which you are sitting. Okay. Then U cross V is perpendicular to both of them, right? So, it will point in the in the height, right, of your room, right? And here, right hand rule is quite important. We will talk about it in the next lecture. But what is the right hand rule? Right hand rule is, I want you to look at your right hand. You curl your fingers from U to V. The cross product U cross V points in the direction of your thumb, right? Which is the picture that you see here. So U cross V is actually on the floor and U cross V is along the height. So this is how the picture will look like. We will talk about it, as I said, in the next class again. But right hand rule is important here. Okay. Now finally, let us look at an example. So find all vectors orthogonal to the two vectors U and V. So we know that U cross V is orthogonal, right, to U and V. So you just compute U cross V. You know that U cross V is I, J, K. You write the components of U, components of V, and you get this answer, right? So this is U cross V. But is that all? Are these all the vectors which are orthogonal to U and V? Now, if U cross V is orthogonal to this, any scalar multiple of U cross V will also be orthogonal to U and V, right? Any vector in that direction will be perpendicular or orthogonal. Now the question is there any other vector other than the scalar multiples of this vector which are orthogonal to both U and V? So I will leave you with this thought. It will be discussed in the tutorial, but think of it pictorially. Okay, so if you have a vector which is perpendicular to two given vectors, U and V here, will you always get a scalar multiple of this vector or can you get something else? Okay, so let us stop here.